Hello, myself Dr. VJD Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss the problems related to input-output programming. So, depending upon the three levels of programming languages, the low-level languages can be the assembly language or the machine language, and the middle level language and the high level language. So here how the assembly language can be used for input output programming can be discussed in this video. The first problem statement is the following program is stored in the memory unit of the basic computer. Show the content of AC, PC, IR in the hexadecimal form. So, three registers can be considered AC, PC and IR. At the end of each instruction is being executed. So, the first execution is CLA, clear accumulator. Next, adding a value. Next, branch uncondition, halt, and the value. Branch uncondition with the address. So, here these instruction after executing of each instruction, how the values of AC, PC, IR can be updated. So this is the AC, PC and IR register values. So CLA, clear accumulator. So accumulator value has to be loaded with 0. Next, add 016. So this 016 value has to be added with the accumulator. Next, branch 014. So BUN means branch unconditionally. Before branching, the PC value has to be hold the return address. So here PC can hold the return address 014. Halt means stopping the values. Next, and operation has to be performed with 017 with the accumulator value. Next, BUN, branch unconditionally with the address of 013, so that the return address of 013 can be stored in the PC. Okay, so like this, the after executing each instruction, the values in the registers can be updated. Next, the following program is a list of instructions in hexadecimal code. So the computer executes the instructions starting from the address 100. Starting address is 100. What are the content of AC and the memory word at address 103 when the computer halts? So these are the instruction location, memory location and the instructions. So here 100 which can be the 5103 instruction. So the 5103 instruction has to be catched with BSA. Next 1017200 which is a CMA. Next 1027001 is the halt. Next 1030000 is the halt. Next 1047800 is the CLA. Next 1057020 is increment. And branching with the location of 103. Branch unconditionally with the 103. So what is the value? What is the content of the accumulator when the address at the 103 when the computer halts? So after executing these instructions one by one during the halt, what is the value of the accumulator? So here accumulator value can be the 5101. So after halting, the accumulator value is 5101 and which is the during the halt the instruction is at the return address of 103. 103 can be specified with the branch unconditioned state. So during that time, the complementing of a CMA instruction can has to be performed at the branch location, so that the value complementing of the 5101 is this, and this is the content of the accumulator. Next is list the assembly language program of the equivalent binary instructions generated by a compiler from the following Fortran program. Assume integer variables all are. Sum is equal to 0, sum is equal to sum plus a plus b, diff is equal to diff minus c, sum is equal to sum plus diff. So to represent these operations, list the assembly language instructions. So here CLA and store the sum before initializing the sum is equal to 0 and load the sum. So this is the execution of the instructions. Sum is equal to 0. Next instruction is sum is equal to sum plus a plus b. So here add a, add b. So that it can has to be stored in the sum, so that the second instruction can be executed. Sum is equal to sum plus a plus b. Next load C, CMA and increment. So diff is equal to diff minus C. Add the diff. Next store the diff. This is the third instruction execution. And fourth instruction execution is sum is equal to sum plus diff. So load the sum in the accumulator with the sum and add the difference, so that the fourth instruction can be executed. So these are the sequence of instructions for the assembly language for equivalent of this Fortran instruction. Or we can use this more efficient optimized mission code with LDAA, add B, store sum, LDAC, CMA, INC, and add diff. This is the second instruction. Next, STA diff, add sum, and STA sum is the fourth instruction. So in this way, the assembly language instructions can be used to represent the equivalent Fortran code. Next, can the letter I be used as a symbolic address in the assembly language program defined for the basic computer? Justify the answer. So a line of code such as LDI is interpreted as an assembler. So two symbol fields which has I as the symbolic address. So LDAII, if you used, it is interpreted as 3 symbol field. So the second symbol is an indirect field to get the effective address of the operand. So we can use the I in the assembly code to represent the indirect address in order to get the effective address of the operand. Next, a line of code in an assembly language program is as follows. DEC 35. Show that 4 memory words are required to store the line of code and give their binary content. Show that 1 memory word stores the binary translated code and give its binary content. So here we have to store the DEC-35. So the character DE has to be used and take a 1 word of the memory. So this is the binary equivalent. And C has to be C and space can be taken 1 word of the memory. Next, -3 can take 1 more word of the memory. Lest 5 and the enter key or carriage written can take the next word of the memory. So 4 words of memory has to be occupied. And 35 equivalent binary code has to be represented with the register line of code of 4 word bits. So this is the representation. Next problem statement, list the assembly language program of the equivalent binary instructions generated by a compiler for the following if statement. So if a minus b 10, 20, 30. So the program branches to the statement 10 if a minus b less than 0, to statement 20 if a minus b equal to 0, and to statement 30 if a minus b greater than 0. So to represent this logic, we have to specify the assembly language instructions. So here first we have to load the b value and CMA the accumulator increment in order to find the difference. A minus b value in order to calculate CMA and increment the value. Add A. Next, SPA, skip if accumulator can contain the positive value. Skip, SPA means skip if accumulator contains the positive value. Next, branch to address 10. So, branch unconditionally if A minus b less than 0, go to 10. If A minus b value is less than 0, then go to the value 10. Next, SJDA, that is skip if accumulator contains the 0 value. Next, branch BUN unconditionally in 30. That means if A minus b greater than 0, go to 30. A minus b greater than 0, then it has to move to the address of 30. And BUN N20 if A minus b equal to 0. So in this way, the conditional logic has to be implemented with the help of checking the accumulator content with SPA, SJDA, and moving the program flow to the specific address with the help of BUN branch unconditional instruction. Next problem statement, explain in words what the following program accomplishes when it is executed. What is the value of location CTR when the computer halts? List the address symbol table obtained during the first pass of the assembler. List the hexadecimal code of the translated program. So this is the problem statement. Here the code is given, and whenever the code has to be stored and branching to the specific locations during the first pass of the assembler. And we need to explain the words, the flow of the program, and what is the value of location CTR when the computer halts, and also what is the hexadecimal code of the translated program. So the program counts the number of ones in the number stored in the location WRD. Okay, so here what are the counting value that has to be taken care with the number of ones that are stored in the location WRD. This has to be stored when the computer can be halted. Since WRD is having the value of 62C1, this is the hexadecimal value that can be converted into binary. And number 1 is the number of ones is the count can be the 6. So CTR value can be the 6 in the hexadecimal form. 6 can be represented. Next, write a program loop using a pointer and a counter that clear to 0 the content of hexadecimal locations 500 through 5FF. So here 500 to 5FF, totally 256 locations are there. So here first we have to initialize the pointers by loading and storing the pointer values into the accumulator. And CTR has to be initialized to 256. Why? Because total number of locations are 256. and storing a 0 to the pointer. And here checking whether the accumulator contains any 0 value or not. And depending upon the checking of the counter value and pointer value, branching to the LOP location. And here ADS, PTR, NBR, CTR are used to represent the hexadecimal form of 500 to 5FF locations. So here the content of hexadecimal locations are from 500 to 5FF. So here 500 to 5FF 256 locations. So here it has to move to the CTR has to be moved to the 256 locations. Next, write a program to multiply two positive numbers by a repeated additional method. So here multiplication has to be done by repeated addition method. For example, to multiply 5 into 4, the program evaluates the product by adding 5 4 times. 5 plus 5 plus 5 plus 5. So in this way, you have to write the assembly code. So here loading the multiplier to the accumulator. And here if it all it is the 0, branch to MZR. So here complement the accumulator INC is to find the difference of the counter. Next, here we have to loop adding and incrementing the value and again adding by this LOP has to be looped. So add the multiplicand here. And the repeat loop has to be done with the branch BUN unconditionally LOP. So the 4 times or how many number that is the multiplier A times. This loop has to be repeated in order to find the addition, continuous addition form. And the multiplier has to be done until repeat the loop until the multiplier times. Next, write a program to multiply two unsigned positive numbers each with 16 significant bits to produce an unsigned double precision product. So here we have to clear and loading the accumulator with Y value and circularly right shift the Y value. So here we have to write a program to multiply two unsigned positive numbers. Next, you want to check whether the value is equivalent to 0 or not. If it is 0, you have to branch to 1. So in the 1 branch condition, we are finding the double precision addition value x plus p. So here loading the accumulator with x and adding with the p, storing the sum into the again accumulator. So with the XL, that is the double precision addition has to be performed in the one label logic. Next, in case of zero label logic, double precision left shifting, the upper higher part of the resistors has to be added here. The lower part can be taken care by one loop. This is the L part of the resistor can be taken care, and ZRO has to be branching can be taken care with the higher part of the resistor. And for repetition, the loop can be taken 16 times 16 significant bits. This operation has to be looped. So that's why branch the loop until 16 conditions. Next, write a program to multiply two signed numbers with negative numbers being initially in signed 2's complement representation. The product should be single precision and signed 2's complement representation if negative. So if multiplier is negative, takes the 2's complement of multiplier and multiplicand. So counter can be 7, P is 0, and here checking the sign of the multiplier, whether it is negative or not. If it all negative, we have to find the 2's complement of this multiplier. So the 1's complement plus 1, 2's complement can has to be find and proceed for the multiplication. Write a program to subtract two double precision numbers. So here double precision numbers can be considered. So here we have to check the lower part of the number can be considered here to save the carry. And along with the carry, the addition can be performed. So here after loading the value, BL value to the accumulator, CMA and increment. So the 1's complement form can have be added here. So the lower part of the register can be considered here. And here after the higher part of the register can be considered in this instruction set. Next, along with carry, the odd operation can be considered. Next, write a program that evaluates the logic exclusive OR of the two logic operands. So, you have to perform the exclusive OR operation. So, loading the value, Y value, and complement it, the accumulator, and with CMA, and storing the value. Next, LDA with X value and complement the Y value, and operation can be performed. And CMA the accumulator. So here X Y complement plus X complement Y. So here Y value and complemented, and it can has to be ended with X. So the term XY complement can be evaluated until here. Next, we have to obtain the X complement, X complement and with Y. So X complement Y can be evaluated with this statement. Write a program for the arithmetic shift left operation branch to overflow if an overflow occurs. So this is the right shift operation. So how this logic can has to be accomplished is by checking the E value extra bit generated or not, the overflow is produced or not. If it all overflow is produced, then accumulator can has to be accumulator value can be checked. If it all 1, it can be okay, the overflow is generated. Otherwise, the accumulator value can has to be checked. If it all 1, then the OVF can has to be overflow is condition can be occurred. So the X value can has to be first loaded, CLE, next CIL, so that SZE, that means the E value can has to be checked. Skip if the E contains the 0 value. Skip if the E flip-flop contains the 0 value. Otherwise, E value can be 1. So, branch to 1. So, here SNA. So, skip next if accumulator is equal to 1. And we have to indicate that with a E value as 1 and the AC value is 1. So, it is a overflow condition. So, branch overflow. So, in this way, the overflow can be identified. Write a subroutine to subtract two numbers. In the calling program, the BSA instruction is followed by the subtrahend and minuend. The difference is returned to the main program in the third location following the BSA instruction. So, this is the calling program, this is the subroutine. So here BSA sub, so that the value has to be moved to the subroutine. So here the subtraction is to be carried out, and here branch to sub has to be repeated, and CMA and in value can be taken, and checking the value of whether it is 0 or not, the accumulator value, and storing the value into the accumulator, BSZ and the branch. The subrahand and values has to be moved. The return difference can be represented here in the calling program. Write a subroutine to complement each word in a block of data. In the calling program, the BSA instruction is followed by two parameters: the starting address of the block and the number of words in the block. So here the starting address and the number of words has to be given as arguments for the subroutine. So here it has to complement each word with the number of words can be passed as here, and here each word has to be complemented with the help of CMP statement. Write a subroutine to circulate E and AC 4 times to the right. If AC contains hexadecimal 079C and E is equal to 1, what are the content of ACE after the subroutine is executed? Okay, so 4 times the circular right operation can be implemented according to the program. So what is the content of AC and E value after 4 times circular right shift? So 079C is the AC content. After 4 times circular right shift, it can give you the 9079. Next, write a program to unpack 2 characters from location WRD and store them in bits 0 through 7 of locations CH1 and CH2. Bits 9 through 15 should be contain 0. So here only this can be a storing of the continuous bits. So 2 characters from location WRD, those has to be stored between the 0 to 7 location. So after storing those values, the subroutine can be called at the location of 8. And store them bits 0 to 7 of location CH1, CH2. Bits 9 to 15 can get the zeros. So the remaining CH1, CH2 can be moved, and the remaining bits can be the store the values of zeros. So these are the some problems that I have discussed regarding the assembly language programming and subroutines by taking the reference of textbook Computer System and Architecture by Maurice Mano. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.